Okay, so real quick, before we get into the code and stuff, I just want to talk about the experiment. So pretty much the experiment is we have an RC servo, right, which looks something like this. So essentially, it has a little rotator, which is connected to a motor inside, and essentially this rotator, all it's going to do is going to rotate 180 degrees, right? So that's what we want it to do. We want it to rotate 180 degrees, and we want it to do it at a 5% pulse width increment. So we'll learn more about that as we continue the video. So you want a pulse width increment and a pulse width decrement, right? 5% pulse width increment and 5% pulse width decrement. So yeah, and pretty much what we're going to be doing is we're going to be feeding in a PWM signal into this servo here, and yeah, that's how we're going to tell it to essentially rotate those 180 or about 180 because some servo motors since it's not digital, essentially since some servo motors are not digital, it can affect the way it rotates because we're obviously dealing with more mechanical things rather than digital electrical stuff. So yeah, so I'd say about 180. So it'd probably be like 160, 170. So about 180. But yeah, so let's get on to the experiment. Okay, so before I get into the code of the experiment, I want to talk about the PWM setup. So as you can see here, here in this commented section, I basically have all the information that we need for to establish our code. So pretty much, right? First, it's essential to know what port and pin that we're going to use to output our signal. So we're going to use port G, pin 1. That's why it's PG1, right? And then the next thing that we know is that PG1, right? The PWM, it's a PWM module 0. It's a generator 2. And the output PWM for it is PWM 5. Okay, so now that we know, so far that we know that information, we could set up the first part of the code. So first we have to enable the clock for PWM modules, right? And we know that the PWM module is 0, as I stated here below before, right? Cool. Next, we enable the set clock divider, right? So the setup clock divider for the PWM timer. So that's what I'm doing here. Okay, now from the information here, right, we know that our system clock is 16 megahertz, and I chose the PWM divisor to be 8, and the frequency for the PWM timer uh, is 2 megahertz, and the PWM frequency is 50 megahertz. Okay, so with that information, we could calculate our load and our CMP, right? So yeah, so let's look at the next part of the code. So pretty much here, right? Again, this is basically setting up our divisor of 8. Then here I disable the PWM generator and set to countdown mode. Then here I essentially use the load and the CMP that I'll find. And yeah, so real quick, let's see how I did that. So let's get to it. So let's talk about how to find the load and the CMP value, right, for our setup for. Okay, so pretty much to find our load, essentially we have our system clock, right? So that's 16 megahertz, and we have to divide that by our divisor of 8, right? And then that's going to be our FPWM timer. Whoops, it's going to be our FPWM timer. Okay, now that we have our FPWM timer, to find our load, what we do is we essentially get our FPWM timer, right? And then set it over, so our FPWM timer, so I'll just bring that down, hertz over 8, and then we divide it by 50 hertz, right? Because I had previously mentioned why in the code, so when I was talking about the code. And then the total that we get is 40,000, right? We get 40,000. Now, if you remember, when to find a load, we have to check that it's less than or equal to 65,535. And again, this number, we get it from the, because it's a 16-bit, right? And if we do that, we get that. That's how we get that number, because it's 16-bit. Okay, so yeah, so that's how we find our load, right? So this is our load. Okay, cool. So now we need to, okay, so now the next thing to do would be to find our CMP, right? So how do we find our CMP that we're given our load, right? So we have our load, which is something that is really needed. Okay, so to find our CMP, right? For our CMP, we need our load times, right? Like this, times 1 minus our duty. Okay, so what is our duty, you might ask? Okay, so our duty is pretty much, so this is going to be our load, right? So we're just going to plug that in there. And then our duty is pretty much the pulse width at a degree, I'll call it degree, over 20. Because each pulse width takes over a degree of 20 seconds. Okay, so now that we have that, right, now that we have that, we know that the CMP was most likely be for the CMP of 90 degrees. And based off some knowledge or some given information, we know that that the pulse width at 90 is 1.5 milliseconds. So if we do 1.5 milliseconds over 20 milliseconds, we do that division. Give me a second, let me plug that into my calculator. We get 0.05. So we get that, right? So that's going to be our duty. So now to just simply get our CMP, we get our CMP is equal to the load, which is 48,000, times 1 minus 0.0075, and we get the total to be, we get the total of that to be 37,000. So yeah, so that's going to be our CMP value. So we have our load and our CMP value. Okay, yeah. So now, cool. So then, now in this next one here, now that I talked about how to find the CMP and the load, now we know that it's a generator B, right? That's why, as you can see here, there's a B, and there's a B here as well. And again, just a quick reminder, there's a 2 here because we know that it's a generator 2, right? As we saw from here, it's generator 2. Okay. So yeah, so, and then in this piece of code here that I was previously highlighting, this here, right, we know that it's a left align, right, that it's a left align signal. And pretty much what this is saying is that when the counter is equal to the load, right, or is getting close to the load, we make the PWM signal equal to logic 1 or high, and when the counter is equal to the PWM value, when the PWM signal is close or equal, we set the PWM equal to logic 0 or low, right? So that's basically what that's saying. Cool. Next, we enable the PWM generator, right? And then lastly, we enable the PWM output. And again, we get this PWM5 from up here, right? And all this information is it can be found in this information here. Whoops, sorry about that. This information here can be found in our chart that that is linked in the lab report. So yeah, okay, cool. Next, they just set up GPIO. So again, our port was going to be port G pin 1, right? And yeah, so pretty much we have to enable the port, right? We have to enable the clock for the GPIO module. So again, we use port G. Then we have to allow time for the clock to stabilize, right? So that's this while here for port G. And then we have to set the port control register of port G, right? And then we get this 0x6 from the chart again. So yeah, and from up here, this is the information that we're given for the PCTO. And then we set up an alternate function, right, for selection bits. So that's for pin 1 again, right, because of PG1 or the port G, pin 1. And then we have to enable the register for all the GPIO pins. Okay, so that's that. And yeah, so now let's look at the actual code for the experiment. Okay, so for the actual code of the experiment, right? So as you see here, we have all our, we included all our files and all our EasyTibia library, right? Cool. And then we had our setups, our functions that we from our the setup PWM and the setup GPIO. Cool. So really quick, I set up this bool direction, this variable, and I set it equal to 1, and we'll see why in a little bit. So yeah, so then now I have here my variables, right, which is CMP at angle 0, CMP at angle 180, and the CMP, right, the CMP that we've found. Okay, cool. So then we have our two functions that we had set up before, right, the ones that we're using, the setup PWM and the setup GPIO. Then here, right, I initialized the values for my CMP value for 0 degrees and my CMP value for at 180 degrees. Okay, so really quick, let's see how I got that. Okay, so now let's see how to solve for the two variables that I found for CMP's 0 at 0 degrees and CMP at 180. Okay, so first, right, we know that our pulse width is from 0.5 milliseconds to 2.4 milliseconds. So the pulse width when it's at 0.5 milliseconds is for the 0 degree mark, and for the 2.4 milliseconds is for when it's 180, right? And from what we recall from when we were calculating the CMP for our setup, right, we know that there's these equations that could essentially help us out, right? These two equations here. So we're basically going to do the same thing. So we know our pulse width, right? Our pulse width at the degree of 0 is 0.5. We divide it by 20. We get 0.025, right? And then we previously found our load. So we're still going to use that load here. And we're going to plug it in. And we get 39,000, right? And we're pretty much going to do the same thing for at the degree of 180, right? So we solve for the duty, right? As we had said that the duty at the pulse width, at 180 was 2.4 milliseconds. We divided by 20. So I had previously mentioned why it was divided by 20, and then we plug in to find our CMP. We plug in our load and our CMP duty that we found, and yeah. So pretty much this is the range for the CMP duty, right? For the CMP, my bad, for the CMP. This is our range for the CMP. It has to be between these two, right? And just to double check that these are right, our CMP that we found before has to fall in between these two. So as you notice, right, our CMP, which is 37,000, which we found last time over here, 37,000, does fall in between this, and that's correct because if we recall, our CMP of 0 degrees has to be greater than or equal to the CMP that we solve for, and that has to be greater than or equal to the CMP at 180 degrees, right? And if we look at it, right, the CMP at 0 degrees is 39,000, the CMP that we found was 37,000, and the CMP at 180 is 35,200. So yeah, this is correct, right? So we know that we solved it correct. Okay, let's get back to our code. Okay, now now that I found the two CMP values for 0 and 180 degrees, right? I then set my CMP equal to CMP 0, so I initialized it to be CMP 0, right? And then we get into the while loop, right? So in this while loop here, right, I set the CMP, the CMP be equal to the CMP, which is at this point it's CMP 0, right? Okay, and then next I set up if statements, and this is where the Boolean variable of the direction comes in. So if the direction is 1, and I considered 1 in this case to be going in a positive rotation, so the positive rotation would be going from 0 to 180 degrees, so that's why I consider it to be 1. So if the direction is 1, right, which it was because we had set it up here to be 1, right? So if the direction is 1, then we're going to decrease our pulse width by 5%, right? And the reason how we got 190, right, decreasing by 190, is because we simply just found the pulse width between uh, um, uh, the 0.5 and the this CMP 0 and CMP 180, right? And then we simply multiplied that by 5%, right? Because we wanted the pulse width to essentially what's it called? We wanted to find the pulse width that had a decrease and increase of 5%, right? As each had the change of the CMP values. So yeah, that's pretty much what I did here. Um, and then that's why it's 190. And I will show that right now. So let's show that how I got 190. Okay, cool. Then I said if the CMP, right? So if once the CMP gets to that CMP 180, we're going to revert the direction to be 0, right? So then now once the direction is 0, or the direction is now going from 180, so once the direction is going from 180 degrees back to 0, we have to now increase the CMP value, right? Because now we're incrementing the pulse width by 5%, which we found out to be 190. So yeah, and we're incrementing it, right? And then we said now, as soon as if the CMP value is equal to 0, right? Then we set the direction back to 1, back to positive, in the positive direction, right? So we set it back going from 0 to 180. So yeah, as you can tell, this is basically going back and forth, right? Which is essentially what we wanted in the experiment. So yeah, as we keep going here, right, we have our CMP, which at this point, right, we're updating it, and then we have our delay of 100 milliseconds between each chain, right, of the CMP value. So yeah, that's pretty much it. So now let's take a look at at our results for this experiment. So yeah, let's get to it.
Okay, so now let's look at the results. Okay, so if we notice here, right, we have our microservo, the SG90, and if we look up here, right, we see that it's rotating from 0 to about 170, 160, but that's okay because the reason why it's rotating at that speed, it's because of the fact that it's not a fully digital servo, so um, yeah, it's more of a mechanical servo. So yeah, that's pretty much the reason why it's doing that. So now if we look at our setup, we have our power supply module, right, which is connected to our servo motor, and it's also connected to our Tiva board, right? And if we flip our Tiva board over, give me a second, let me flip it over. Yeah, so as you can see, right, since if we have our pivot board, we now see that it's connected to ground, and the power and ground is also connected to our servo. And from the pivot board, if we notice, right, if we look closely at it, our PG1, right, which is essentially what we had in our code, is essentially connected to our servo motor, right, as we see there. And yeah, so again, just a quick overview of the entire thing. Yeah, and then our pivot board is connected to my laptop, and then the LED module, well, that's connected to the DC to the outlet. But yeah, so that's pretty much it. So yeah, so if you notice, our micro server, right, is if I look at it from the top view, it's rotating, right? So if you notice, at that point there, it's 0, then it goes to 9, and it goes to about 170, 160, and then it goes back, right? We pretty much did want this, so we wanted exactly this to happen because of the fact that, again, it's simply just rotating, right? It's not a full digital servo, as I had previously stated. So it's fine that it just goes all the way to like 160, 170 instead of the complete 180. So there's eventually like some type of I guess you could call it lag, or unfortunately there's some type of like difference between that when it gets converted. But yeah, it still works, so it still rotates back and forth. Yeah, so as you could tell, if we notice, as it's spinning, right, as we notice here, pretty much it has an increasing, so when it goes from 0 to 180, right, it has an increasing, I mean, it's decreasing basically, right? It's decreasing the CMP value by the pulse width, right? It's decreasing the pulse width by 5%, as we noticed. And then when it goes from the well, in this case, it's like the 170, 160 degree mark, but in mathematically we did it from 180, right? If it were to go back, it basically increases the pulse width by 5%. So yeah, as it's going from 0 to 180, it's decreasing the pulse width by 5%, and then as it goes from 180 to 0, it essentially increases the pulse width by 5%. So yeah, as we notice, it's rotating back and forth from 0 to about 170, but we had set it up for 180, but it's still okay like that. And from about that 170 degree mark back to 180. So yeah, that's pretty much it.